seem complicated, but there's a reason why if you go to college and you're going to be a civil engineer or a mechanical engineer or even an aerospace engineer, you'll have to take at least one full semester of statics. You may have to take 2 semesters of statics depending on which year you're in or which program you're in. Statics is quite literally, though, just two things. Net force equals 0 and net torque equals 0. And for the most part, at least all the examples we're going to do, also will have velocity equals 0 and angular speed equals 0. So when we're talking about something that's statics or in static equilibrium, it is not moving. It is experiencing balanced forces and balanced torques, but it's not moving. Now, this example I put here is on purpose. It's I guess the word I want to use is that it's symmetrical. And the reason I want to start with the symmetrical one is mostly just to figure out what the mass of the meter stick is before we get started, before we go any further. And we can do that from this because we know net force is 0, and there's only one downward force, and that is the weight of the meter stick. So the weight of the meter stick is here. I have 2 upwards forces, and I'm going to go ahead and say that the tension for the 20 centimeters is just T20, and the tension at 80 centimeters is T80. And we can actually read those straight off the screen. Let's make sure we know which one is which, though. Is that force 1? So force 1 is this one, so that's our TL. And force 2 is this one. Is that good for you guys? Is that matching up with what I'm seeing? Yeah. All right, so I happen to get them in order. So the top one is TL, and the bottom one is, the top one is T20, and the bottom one is T80. And whether you can read it or not, I can. Right now, T20 is 0.32 newtons, and T80 is 0.32 newtons. That kind of tells me, too, that we are very symmetrical, right? We're having the same value in both of those. So this alone would allow us to figure out what the weight of the meter stick is, but it's only able to do so because we have a perfectly symmetrical system. That's why we're able to do it. So if we look, we have 2 upwards, T20 plus T80, and 1 downwards, the weight of the meter stick, and they have the sum to be equal to 0. Now, this part, pretty easy. The weight of the meter stick has got to be 0.64 newtons. So I don't think that part's particularly hard, right? Just add those two things up, the 0.32 and the 0.32. So not hard. But here's the thing. I have a 500 gram mass here. And this part I don't think is going to be a surprise. If I hang it at the 50 centimeter mark, I suspect both of these will increase the amount of upward force necessary for the system to remain in balance, but they're going to do so symmetrically. So let's try that. I'm going to take this, it's 500 grams. Placing it at 50, and I am not surprised by the results here. 500 grams is 5 newtons, so placing 500 grams increases both of these by about 2.5 because it's right at the center. Does that make perfect sense? The issue isn't this example. The issue is what happens when we take this and say shift it to one side or the other. Is it can you make an easy prediction that if the weight is over here more, this is going to have to pull upwards more than this one because it's going to be closer to this particular support? Now herein lies the issue. The moment I start doing that, and I just placed it randomly over there, that should be clear that one side is pulling up with more tension than the other side. How do we know how much? One of the problems with just using force is that we have 2 upwards forces, and we don't know how much either of one of them is going to be before I actually create the model. So let's say I want to place it at 60 centimeters, or I want to place it at 30 centimeters. No matter where I place it, I should be able to predict how much tension is going to be in either side. But force won't be enough to do so. Let's just put out an example. Let's say that I have that 500 gram weight and I put it over here at the 70 centimeter mark. So this is going to be my 5 Newton mass. Since I now know that the weight of the meter stick is, I don't want that to look like an omega, so weight of the meter stick is 0.64 newtons. Knowing this isn't enough for me to figure out what the two tensions are if I use just force alone. Because if I use just force alone, I'll find that T20 plus T80 minus the weight of the meter stick minus my 5 Newton mass equals 0. Solving this for T20 and T80 is going to give me that this equals 5.64 newtons. But that's clearly not enough for me to distinguish T20 from T80. In order to complete a statics problem, statics problems are going to involve both net force and net torque. The net force part's pretty easy, but it generates a relationship that will tell us only the up and down portion or the left to right portion of forces. But we're going to need the rotational stuff in order to figure out the individual forces themselves. This is how a statics problem is done. Now, there are some things we have to do different. Force problems, in the past, we've drawn a free body diagram for them. You guys do remember all that stuff from before. You'll notice I never drew a free body diagram for this, partly because I really didn't have to. It's just a couple of up and down arrows. But torque's a little different. Torque requires that we know where the force is applied in order for us to calculate a torque. So we won't always draw a free body diagram. Often we will draw something representing the object experiencing the torques. And then from there, we'll go through and try and decipher what the size of each torque is. So let's do that here. I have my meter stick, and I have 4 forces displayed upon it. I obviously am doing the net force problem, and there are no rotations happening. These torques aren't causing the system to rotate. But in order to do a torque problem, we are going to have an axis of rotation, even though the system isn't rotating. So something to, if you're trying to create like set of steps on what to do, well, you'll establish your net force problem first, and you already know how to do that, so I don't have to explain those steps. But for a statics problem, you're going to have to start a net torque problem as well, and you'll set the net torque equal to 0. That's step 1. Step 2, and this part's a little bit more complicated, but not much. You'll have to choose a pivot point. You'll have to choose a pivot point. You have to place the fulcrum somewhere in your system. But because the system isn't rotating, you can place the fulcrum anywhere you want. Again, you have to choose a place to put your pivot point. But because the system isn't rotating, you have to place the pivot anywhere you want in your system. So step 2 requires that you place the pivot point someplace on your diagram. I've said it 4 times, and I've watched exactly who wrote it down and who didn't. Please, just write that down. You'll want that bit of knowledge. It's useful. You won't remember. You think you will, because it seems so obvious, but you won't. Now, a little hint for step 2. If you want this to go easier, the best way to deal with step 2, if you can, is to eliminate an unknown using your pivot point. Since you get to choose anywhere you want to be your pivot point, you want to try and eliminate one of your unknowns in calculating or in placing your pivot point. For me, just looking at my example, I have 2 unknowns. The tension at 20 and the tension at 80 are both unknowns. So if I want to if I want to place the pivot point someplace, and again, I can place that pivot point anywhere I want, I think it best to place it someplace where I eliminate one of my unknowns. If I place the pivot point at the location where one of the tensions is, the torque arm goes to 0, and that eliminates that particular torque from my calculation. Again, because it's not actually rotating, doesn't matter where you place the pivot point. You can place the pivot point in the middle if you'd like, but that eliminates a force that you actually know. and it's going to generate a relationship that has two unknowns in it. That's okay because we already have one relationship that has two unknowns in it. But if you can eliminate an unknown, you're certainly going to make your problem easier. So if it were me, I'm going to take that pivot point and I'm going to place it right here at the 20 centimeter mark where one of the tensions already exists. Now that does leave me with three other forces acting on the meter stick, which means I have three other torques. So I will have torque for the meter stick, torque for the 5 Newton weight, and torque for the 80 centimeter tension. 3 torques. So step 3 is to sum all of your torques together and set them equal to 0. That also means laying out each individual torque. And if you don't remember, torques have 3 parts: torque arm length, size of force, and the angle of attack. The 3 parts of each of our torques. So let's take each part one at a time. Let's start with the meter stick. The weight of the meter stick acts as a torque. And our first thing is to come up with something that represents the torque arm length. The torque arm is going to be from the pivot point to where the force is applied. So that's from the 20 centimeter mark to the middle of the meter stick. That's at the 50 centimeter mark. So my first torque arm length is going to be 0.3 meters. Next, I need the size of that force. That's just going to be the weight of the meter stick, which we already know is 0.64 newtons. Lastly, we have to determine the angle between the force and the torque arm. Is it pretty clear that in this instance that's going to be 90 degrees? Excellent. Next, we have to decide whether this torque is positive or negative. Now, that suggests we have to come up with a way of deciding which torques are going to be positive and which torques are going to be negative. We could use the whole right-hand rule thing to figure out direction, or since we're all facing this from the same direction, we could make it just clockwise and counterclockwise. That's still fine. If we all have the same vantage point, that still works. So right now, this torque looks like it's a clockwise torque because it's going to be causing it to go in a clockwise direction. Do you want clockwise to be positive or do you want clockwise to be negative? You just have to pick one. You want it negative? Alrighty. So clockwise is negative. Now, clockwise is into the board. That's the direction of rotation, is into the board for clockwise, and we are making clockwise negative. So I'm stating that here so that we know any counterclockwise torques will be positive. All right? You lay out the other 2. I did one with you. You lay out the other 2. And I'll pick 2 people to kind of tell me what they wrote down for each of the 2 torques that are left. All right, so I walked around. A lot of you have this. So I got this distance, 0.5 meters, and this is 5, and this is sine 90. And this is also negative because it's causing rotation in the same direction. Good job. From 20 to 80, I saw almost all of you figured out that's 0.6. Good job. Way to go. I saw a lot of different things here, but I'm using the symbology that I have, which would be the tension. So some of you wrote different things there, normal force, stuff like that, but it's a tension technically. It's also going to be sine of 90. And this one's going to be positive because it's causing a counterclockwise torque. So, yeah, you guys are right to jump into the calculator part here because, yeah, you're just solving for the one unknown. We're going to add all these together and get us our one unknown. So 0.3 times 0.64, I get 0.192, so that's negative 0.192. That's meter newtons, but I'm going to leave the units out for this part. plus 0.5 times 5, that's going to be negative 2.5 meter newtons. And then lastly, plus 0.6 times T80 equals 0. And now we're just solving this for T80. So I'll get that 2.5 plus 0.192. And that's going to be 0.6 T80 I get equals 2.692. So T80, when I divide by my 0.6, gives me 4.9 newtons. No, I'm sorry, 4.49. This isn't it. You still have to find out what the other tension is. This just gave you what T80 was, but we know that T20 plus T80 equals 5.64. Right, so we're just taking what we found here and plugging it in here to get our other tension. And I get a 1.15 newtons. All right, let's try it out. We still have our two supports, one of them over here at the 80 centimeter and one over here at the 20 centimeter. So this will be T20 and this will be T80. We also have our downward force in the middle, the weight of the meter stick. But we're talking about now taking and placing our weight, say, somewhere over here. And we don't know what this distance is. Trying to figure it out. So I want to find the threshold distance. What is the distance where I can place the 5 Newton weight where this tension will just be making it to 0? And by the way, you did this in the lab already. In the lab, you did this to measure the mass of the meter stick. We're just turning it a little bit. You want to find a system where it goes into balance without a tension necessary here. That's all this is. But see if you can find where that exists. A few of you are a little stumped. The net force one, we may or may not need. That's going to be T80 minus 5 minus 0.64 equals 0. And that's we're letting T20 go to 0. So we're dealing with the fact there's only one force acting upwards. That's the one support. And the other two are acting downwards. That tells you what the tension is at the 80, but that's not what you're being asked. So that's not really going to be helpful. So we're going to do net torque next and set the net torque equal to 0. I have to choose a place for the pivot point. I can choose anywhere I want, but to be honest, I think I'm going to choose T80 to be my pivot point location. It eliminates that torque from the equation. And that leaves only 2 torques. Right? Because we're already saying that this one equals 0. So if this equals 0, I don't have to use it as a torque. So I'm going to have the torque from the meter stick and the torque from the 5 Newton, and those are the only ones there. Torque arm length for the meter stick is known. It's 30 centimeters. And the size of the torque is based on the force, which is going to be 0.64 newtons. And again, sine of 90 degrees. I don't know where the other one is. Let's put R. I don't know where that's going to be. But I know that it's 5 newtons. Lastly, the 5 Newton is causing a clockwise torque, so it's negative. And the meter stick is causing a counterclockwise torque, so it's positive. And these have to sum to be equal to 0. So 0.3 times 0.64 minus 5r equals 0. That's it. So I think this is going to be 5r equals 0.192. So r is going to be, I got 0.0384. Is that what you guys got? Well, let's see. As this class is not, it's not particularly deep when it comes to content, we won't do very many statics questions. But if you actually go into engineering and you take a statics course, you will do some pretty crazy stuff. We are dealing with what looks to be a very one-dimensional problem. And I hope that's pretty clear. Even though I know it looks two-dimensional, it's just one thing that has forces acting on it. Ours are all going to be mostly one-dimensional questions. When you start getting two-dimensional questions, you have an object that takes up two-dimensional space and forces are acting on it in multiple directions. That becomes a more complicated problem. But ours are going to be largely one-dimensional. The most likely kinds of questions you'll see are what we just did, but also there will be boom arm questions. Boom arm question has something like a support structure, some kind of vertical support where you have a boom arm. That's what the white thing is, a boom arm. And it might have a cable connected to it. Somewhere along its length. And usually there's a load placed on the system. So the load could be a box or something that applies a force. This is a common question. And one of these questions, again, you're trying to have a system that's going to be in static equilibrium, but we have, in this case, at least one force that's being applied at an angle, because it's going to be the tension in the cable that's going this direction. And then it's usually placed some distance from the support structure. Students often make a few mistakes with a problem like this, so I want to highlight some things about this problem before we get started. The first is that there are the obvious forces that we've talked about for the last example. There's going to be clearly a downward force here from the load. There's going to be a tension that is upwards and to the right. There's going to be the weight of the arm itself, but students often leave out the fact that the support structure is causing a couple forces too. The support structure has at least one force this direction. Well, you can't see that. One force this direction from the wall. This is a normal force from the wall. And then it's not well understood right now, but there's also going to be a force from the wall this way or this way, depending on how the other forces in the system are established. And that depends on the angle that's here, stuff like that. That will determine whether you have an upward force from the wall or a downward force from the wall. But you could have either one, but you have to establish the wall is causing a force both outwards and up or down. And since you don't know the direction, you have to pick a direction. And if you work the problem out where you're asked about the wall, then if you pick the wrong one, you'll get a negative answer. And that just tells you picked it in the wrong direction. But usually the question that is asked is something like, what is the tension in the string? Or they'll say the string can only hold this many newtons. Where can you place this mass? It'll be something like that. But this is a common kind of question. The other, and this one can be a little bit harder, but it really isn't that much more difficult. But it's a ladder question. If you've ever used a lean-to ladder, you know that a ladder has on it usually a picture that says, here's the approximate angle that you should lean the ladder for it to be the most stable. Ladder questions can be tough because of the number of possible forces acting on them. So as we look at the ladder question, assume maybe that you're climbing the ladder and you might be standing, say, here. How many forces are you thinking are acting on the ladder? Maybe take a minute, draw this out, and identify what you think the forces might be, because you may be forgetting one. Maybe forgetting two if you're not careful. All right, in identifying forces, did you identify that the weight of the ladder is going to be a force? And did you identify that the load applied by the person is going to be a force? Did you identify a normal force from the ground? Did you identify a normal force from the wall? Did you identify friction from the ground? Did you identify friction from the wall? Those are probably the forces that are acting on our system. This problem is generally done at your level, excluding the friction from the wall. If you exclude the friction from the wall, this is not a particularly hard problem, but with the friction from the wall, that ramps up the difficulty actually quite a lot. There's two things I do want to point out. If we do leave out the friction from the wall, there's two different angles that all these forces are acting on. Do you guys see that? There's going to be this angle on one side and its complement over here, because those two angles aren't the same. You'll need some information about the angle. And one of the things I talk about when doing this problem is it might be easier for you to take the ladder, draw it horizontally, and then consider each of these forces as they act on the ladder, and choose your pivot point wisely in doing a problem like this. Because you'll find that if you can take those out and start identifying where those forces are, that some places are better for a pivot point than others. Like you might find in working the problem out for the torque portion, if you place the pivot point here, you eliminate two forces that, well, at least one of them is probably an unknown, because the kind of friction that's acting here is static friction, which you're likely not aware of how much friction you have to work with. In fact, a common question is, where can you safely stand before the friction isn't enough to hold the ladder in place and the ladder slides out from under you? This is why there's a little symbol on the ladder, and usually something that says where it's safe to stand and where it's not safe to stand.